In this lesson, we will learn about the Schrodinger equation. This will be our fifth postulate. In earlier lessons, we learned postulate 1 of quantum mechanics, which says that there is a function associated with the system, represented by the Greek letter psi, and called state function or wave function, that has all accessible information about the system. We also learned with postulates 2 through 4 how to extract information from psi using operators. In this lesson, we will learn in general how to determine psi with postulate 5. Postulate 5 says that the state function changes over time and its behavior over time is summarized by the time-dependent Schrodinger equation shown here. According to this equation, if we take the derivative of psi with respect to time, then multiply by negative h bar over I, what we get should be equal to what we get by applying the Hamiltonian operator on psi. Solving the time-dependent Schrodinger equation means finding the function psi that would satisfy the equation. Just a reminder, the Hamiltonian operator is the operator that corresponds to the total energy of the system. It is useful to look at solutions for simplified cases of a problem first. So let's see if we can do that for the time-dependent Schrodinger equation. Psi is a function of both coordinates and time. Let's see if we can find solutions that can be written as a function of coordinates times a function of time. Psi doesn't have to be in this form, but you will see that things would be a lot easier if we could find some that are in this form. Here we use the lowercase psi to represent the part that depends on coordinates. Without loss of generality, we'll just look at the one-dimensional case where psi depends only on the x-coordinate. Please be aware of the distinction between lowercase psi and uppercase psi. Uppercase psi represents the state function that depends on coordinates and time, while lowercase psi represents just the part that depends on coordinates. So, are there solutions that can be written this way? The answer is yes, if the potential energy of the system does not depend on time. This would be the case if there are no time-varying external forces acting on the system. If you recall, the Hamiltonian operator is equal to a sum of the kinetic and potential energy operators. The kinetic energy operator just involves partial derivatives with respect to coordinates, so it does not depend on time. The potential energy operator is a multiplicative operator, and it depends on forces that the particles in the system feel from each other and from external sources like an incoming electromagnetic wave. So, if the potential energy does not depend on time, neither does the Hamiltonian operator. What this means is that when we apply the Hamiltonian operator on a function, we will just treat time as though it is a constant. Here's the proof. Here's our time-dependent Schrodinger equation. We assume that the Hamiltonian is independent of time. And if this is the case, we can write psi as a product of a function of coordinates times a function of time. We are going to substitute this product, lowercase psi times f, for uppercase psi in the time-dependent Schrodinger equation, here and here. And let's see where it leads us. If we don't encounter any contradiction, then we're okay. Since lowercase psi does not depend on time, we can treat it as a constant when we take the partial derivative with respect to time. So we can pull it out of the derivative. Similarly, since the Hamiltonian operator has no effect on time, we can treat f as a constant here and pull it out of the operator. Remember that the Hamiltonian operator is a linear operator, so we can do this. Now, let's divide both sides by lowercase psi times f. Then simplify. On the left-hand side, lowercase psi cancels out, leaving us with negative h bar over I, f, times partial derivative of f with respect to time. On the right-hand side, f cancels out, leaving us with 1 over lowercase psi times h hat psi. At this point, we can say that both sides must be equal to a constant. Why? We can see that the left-hand side depends only on time, and the right-hand side depends only on coordinates. How can two expressions that depend on different variables be equal? The only way is that, regardless of the values of the variables, both expressions must evaluate to the same constant. Okay, so far we've seen that if the Hamiltonian is independent of time, and we write the wave function as a product of a function of coordinates times a function of time, we can rewrite our time-dependent Schrodinger equation into an equation where one side depends only on time and the other side depends only on coordinates. And this means that both sides must be equal to a constant. Let's call that constant E. It will become obvious soon why we call it E. Here's the left-hand side, the expression that depends only on time, set equal to the constant E. This is a fairly simple equation to solve. We can show that function f is equal to e to the negative iet over h bar. And here's the right-hand side, the expression that depends only on coordinates set equal to the constant e. We can rearrange this to h hat psi equals e times psi. Note that this expression says that applying the Hamiltonian operator on little psi gives us back little psi times a constant. This means that the little psi is an eigenfunction of the Hamiltonian operator and the eigenvalue is E. Therefore, the constant E must be an energy value. That's why we give it the symbol E. Remember that the Hamiltonian is the operator for total energy. This equation, h hat psi equals E times psi, is called the time-independent Schrodinger equation. We have not encountered a contradiction. If the Hamiltonian is independent of time, we can write big psi as a function of coordinates times a function of time. But if we do, the function of time must be e to the minus iet over h bar, and the function of coordinate, little psi, must be an eigenfunction of the Hamiltonian operator. Here's the derivation of the time-dependent part of the stationary state function, starting with negative h bar over if times derivative of f with respect to time equals e. We can show that f is equal to e to the negative iet over h bar. It should be straightforward to show that we can rearrange the starting equation to this. We rearrange it this way to have the two variables on opposite sides of the equal sign. The variable f only appears on the left-hand side. The variable t only appears on the right-hand side. Now we can integrate both sides of the equation. Integral of df over f is natural log of f. Integral of minus ie over h bar dt is just minus ie over h bar times t. We combine the integration constants from both sides into just one, shown here as c. Now we take the inverse log of both sides. The left-hand side becomes f, and the right-hand side becomes e raised to the sum of negative iet over h bar and c. We can rewrite the right-hand side as e to the negative iet over h bar times e to the c. For convenience, we omit e to the c in our expression for f, since we can just account for it when we later normalize the state function. So we end up with f being equal to e to the negative iet over h bar. We just proved that if the Hamiltonian operator does not depend on time, then there are solutions of the time-dependent Schrodinger equation that can be written as a function of coordinates times a function of time. The function of time is e to the negative iet over h bar. The functions of coordinates, represented by lowercase psi, are eigenfunctions of the Hamiltonian operator. These solutions are called stationary states, but why? They obviously depend on time. The reason is that the corresponding probability density function is independent of time. Recall that probability density is equal to the square of the absolute value of the state function. The probability density function is the state function multiplied by its complex conjugate. Psi star psi is equal to little psi times e to the negative iet over h bar multiplied by its complex conjugate. This is just equal to little psi multiplied by its complex conjugate, which is independent of time. Where did the time-dependent part go? The complex conjugate of e to the negative iet over h bar is e to the positive iet over h bar. Multiplying these two gives e to the 0 or 1. For a stationary state, the part that depends on coordinates is called the spatial part or spatial factor, or the time-independent wave function. We have seen that the spatial part is an eigenfunction of the Hamiltonian operator. Applying the Hamiltonian operator on it gives us back the same function times a constant E, which we identify as the energy of the system. How about the entire function itself? Is it an eigenfunction of the Hamiltonian operator? Let's see. Applying h hat on big psi means applying it on the product of the spatial part and e to the negative iet over h bar. Remember that stationary states exist in cases where the Hamiltonian operator does not affect time. So we can pull out the time-dependent factor from the Hamiltonian operator since the operator is linear. As far as h hat is concerned, the time-dependent factor is just a constant. H hat applied on the spatial part just gives back e times the spatial part. Finally, e to the negative iet over h bar times the spatial part is just equal to big psi. Therefore, applying h hat on big psi gives us back big psi times the constant e. So, the answer is yes, a stationary state is an eigenfunction of the Hamiltonian operator. A stationary state is a state with a well-defined energy. Why are we interested in stationary states? Well, we wouldn't have to try to solve the time-dependent Schrodinger equation. By solving the time-independent Schrodinger equation, we can get the spatial parts of the state function and the allowed energies. All we have to do to construct the time-dependent state function is to multiply the spatial part by e to the negative iet over h bar. Furthermore, stationary states form a complete set because they are eigenfunctions of the Hamiltonian operator. We already postulated that operators corresponding to physical observables have a complete set of eigenfunctions. This means that any solution to the time-dependent Schrodinger equation can be written as a linear combination of stationary states, which we just said are easier to determine. We can check if the allowed energies we get from the time-independent Schrodinger equation are consistent with experimental data. Remember that photon energies associated with spectral lines in the emission and absorption spectra of atoms and molecules correspond to gaps between allowed energies. This allows us to experimentally validate the predictions of quantum mechanics. We know that stationary states are eigenfunctions of the Hamiltonian operator. What about linear combinations of stationary states? For example, suppose h hat psi 1 equals e1 times psi 1 and h hat psi 2 equals e2 times psi 2. What happens if we apply h hat on c1 psi 1 plus c2 psi 2? Since h is a linear operator, we can distribute it to the two terms and pull out the constants. We can substitute e1 psi 1 for h hat psi 1 and e2 psi 2 for h hat psi 2. Can this expression be written as a constant times the linear combination? The answer is yes, but only if e1 and e2 are equal, because then you can factor out the energy. In other words, only if psi 1 and psi 2 are degenerate eigenfunctions of the Hamiltonian operator, and the resulting linear combination will also be a stationary state with the same energy. Otherwise, in general, no. How about the time-dependent Schrodinger equation? Would a linear combination of stationary states also be a solution? Let's see. If psi1 and psi2 are stationary states that satisfy the time-dependent Schrodinger equation, then we can say that negative h bar over I times the partial derivative of psi1 with respect to time is equal to h hat applied on psi1. Similarly, negative h bar over I times the partial derivative of psi2 with respect to time is equal to h hat applied on psi2. What if we take negative h bar over I times the derivative of a linear combination of psi1 and psi2 instead? Well, the derivative of a sum is equal to the sum of derivatives. You can pull out constants from the derivatives. Then we can identify this as h hat psi1, and we can identify this as h hat psi2. So we get this expression, which is just equal to h hat applied on the linear combination, since h hat is a linear operator. Therefore, the answer is yes. Any linear combination of stationary states is also a solution to the time-dependent Schrodinger equation. However, if the stationary states are not degenerate, then the linear combination would not be a stationary state, as we have seen earlier.